students. Welcome to today's 11th physics class. I hope you are all doing well. Today, we are diving into a very important and fascinating topic in gravitation, the energy of an orbiting satellite. This concept is crucial for understanding how satellites stay in space and what it takes to launch and maintain them. Okay, so this is a very important one. To kick things off, let me share a brief but powerful story. Think back to 1969, the Apollo 11 mission marked a historic milestone when humans first landed on the moon. Astronaut Neil Armstrong's journey was not just being a big rocket, it was fueled by years of incredibly precise calculation of gravitational forces and critically orbital energies. They had to overcome immense challenges to achieve that. This achievement proves that understanding the principles of gravitation can lead to the extraordinary accomplishments, even reaching beyond our planet. And it has inspired generation to pursue science and engineering. Today's lesson will give you a taste of the physics that made this possible. Now, please make sure your chat box is ready for your quick interactions and your voice settings are working for when I ask for a verbal response. Okay. Okay. Now, let's quickly warm up our minds and recall some prior knowledge with a short quiz. So this is just an icebreaker to get us thinking about the concept we have covered in the previous classes, especially about energy of the satellite and Earth satellites like that. Okay. Okay. I will share the screen now. Second. Sorry. Sorry. Yes. Yes. Okay. Good. So this is a first question. The time period of the satellite in a circular orbit depends upon mass of the satellite, mass of the Earth, radius of the orbit, the speed of the satellite. Already we saw that. We saw it in the previous class. Yeah. So this is class 11th. Already in previous classes, we discussed with orbiting, that is Earth satellites. Now the continuation, energy of an orbiting satellite. Okay. Okay, right. The time period of the satellite in a circular orbit depends on which one is correct. The mass of the satellite, the mass of the Earth, the radius of the orbit, the speed of the satellite. Which one is correct? Yes. 3. Good. Radius of the orbit. Yeah, very good. Then next. Yeah, very good. 11th physics, class 11th physics. Very good. Good. Yeah. So already we know that the time period T is directly proportional to radius orbit of the orbit. Yes, very good. Well and good. Good. Second question. If the height of a satellite's orbit above the Earth's surface increases, its orbital speed, which one is correct? Increases, decreases, remains the same, becomes zero. Very good. 2 or 3 decreases or remains the same. Which one is exactly correct? If the height of the satellite orbit increases above the surface increases, its orbital speed decreases or increases or remains same or becomes zero. Which one is correct? Yes, okay, right. So if the height of the satellite's orbit above the surface increases, its orbital speed decreases. Yes, very good, good. Second option, correct. And the final one, if the distance between two masses is doubled, how does the gravitational attraction between them change? Option A, it becomes 4 times. Option B, it is reduced to quarter. Option C, it is reduced to half. Option C, it is doubled. So, already you know that there is a gravitational attraction force between the two masses. Yeah. But masses are doubled. So, for example, 3 kg. Now, for example, two masses means A and B. A doubled, so 2A. B doubled, 2B. Then what is the gravitational attraction force? 1, 2, okay, 3, 1. It becomes 4 times. Is it correct? Here, you can remember that the force of attraction between the two masses, it depends upon the masses of that planet or masses of the objects, but inversely proportional to the distance. Is it correct? Inversely proportional to the distance. So here means the distance between two masses doubled means distance doubled. Okay, mass is not doubled here. Distance doubled. That means 2r. Sorry, r becomes as 2r. Suppose mass doubled means 2m, but here distance doubled. So you have to careful in that question. So r becomes 2r. Then gravitational force will reduce surely. But option B is correct answer. Yes, 2 correct. Very good. It is reduced to quarter because r becomes into 2r. So r square, already you know that F is directly proportional to 1 by r square. So now r becomes to 2r. So 2r square means 4r square. So quarter times. It is reduced to quarter times. Yes? Okay. V square. Okay. So option, first question, option 3, the radius of the orbit. So here it is reduced to quarter. Yeah. Okay. The time period of the satellite, radius of the orbit, the height of the satellite orbit above the Earth surface increases, decreases. Okay. Its orbital speed decreases. Okay. So once again, I will show the answer because mistakenly I could not select that options. Okay. Okay. Once again, I will show the answer. Yes. Now screen is clear. Now you can check that answers. In previous case, okay, the time period of the satellite in a circular orbit depends on radius of the orbit. The height of the satellite orbit above the Earth surface increases, orbital speed decreases, and the final one, if the distance between two masses doubled, the gravitational attraction between them change is reduced to quarter. Is it correct? Okay, right. Now, times up for the quiz. Let's move straight into the core concept for today. Okay. Yes, satellite. So this is Earth. So here, one satellite is there. A satellite in a circular orbit, like that. A satellite in a circular orbit around the Earth has two main types of energy. One is kinetic energy. One is kinetic energy. Another one is gravitational potential energy. Gravitational potential energy. We can say that potential energy in this case here. Okay, for simplicity, we can say that potential energy. Okay, good. So, a satellite in a circular orbit around the Earth has two main type of energy. One is kinetic energy, another one is gravitational potential energy, or we can say that in the simplicity, for simplicity, we can say that potential energy. Okay, right. First of all, kinetic energy. So, kinetic energy, satellite in motion. Yeah, the satellite is in motion. So, it possesses kinetic energy, which is given by the familiar expression 1 by 2 mv square. Already we know that. Yeah, kinetic energy is 1 by 2 v square. Here, m is a satellite's mass. Satellite mass. Here, v means velocity. That is orbital velocity of the satellite. For the circular orbit, we know that orbital velocity v equal to g m e by r e plus h. Yeah, clear? V square is equal to g m e by r e plus h. Mass of the earth, r e, radius of the earth, h, distance between the earth to satellite. Okay, r e plus h. R is the radius of the earth, h is the distance between the surface of the earth to satellite. Here g is the gravitational constant. Okay, so if we substitute the expression for v square into the kinetic energy equation, we will get the 1 by 2 m here v square. So g m e by r e plus h. Okay, so we can write like that 1 by 2. Sorry. Two r e plus h, and here g m e into m, like that. Okay, so this is a kinetic energy equation for this orbital satellite. Okay, now we will move into the next energy, that is potential energy. Potential energy. Satellite is under the influence of Earth gravitational field. Yeah, so here Earth, so this is a field of the Earth, that is a gravitational field, Earth gravitational field. So here a satellite is there. So satellite is under the influence of Earth gravitational field. So giving it gravitational potential energy. So potential energy formula P is equal to minus G M E M by R E plus H. So this is a expression for potential energy of the satellite under the influence of Earth gravitational field. Okay. Here you can see that negative sign. Remember, the negative sign is there because gravitational force is always attractive. Gravitational force is always attractive. So, Earth attract the satellite towards the center. Already we know that. Okay. So, potential energy is defined to be zero at infinite separation. Okay. Potential energy is defined to be zero at infinite separation. Infinite separation. Okay. Now, total energy. So, total energy is a simply the sum of the kinetic energy and potential energy. Okay. Okay. So, we have the equations for kinetic energy and potential energy. We can substitute here. This is a kinetic energy and this is a potential energy. So here plus, so negative sign for potential energy. That's why I am putting negative sign here. Okay. Re plus H. This is a expression for total energy. Okay. When you combine these two terms, you find a very interesting and simple relationship. The total energy comes out to be, you can see here, you can see that 1 by 2. This is a 1. Yeah. G, G, M, E, M, E, M, M, R, E, R, E, H, H. There is a difference. 1 by 2 here, here, 1 negative sign. So this is a off, this is a whole. Okay. 1, this is off. So 1 by 2 minus 1 gives minus 1 by 2. Yeah. 1 by 2 minus 1 gives minus 1 by 2. So we can write now like that. Total energy equal to minus 1 by 2 G M E M by R E plus H. This is a total energy, which is a combination of potential energy and kinetic energy of the satellite. Okay. Take a moment to compare the three expressions. Again, I will write the kinetic energy and the potential energy here. Then only which is very useful to compare the three quantities, three equations. Okay. Now compare the three equations. What do you see? Yes. Kinetic energy is positive. Total energy negative. Potential energy negative. So kinetic energy only positive. Okay. One point. Next point. Potential energy here is the twice of the total energy. Here you can see that potential energy is twice of the total energy. Potential energy is twice of the total energy because, so suppose here you can multiply 2 into cancel, so minus G M E by M by R E plus H. Yeah. So potential energy is twice of the total energy. So P is equal to 2 into 2 T. Okay. Next one. Kinetic energy and total energy which is equal in magnitude. Yeah, G, G, M, E, M, E, M, M, 2, 2, R, R, E, H, H, but which is equal in magnitude, not a sign, because this is a positive quantity, this is a negative, but which is equal in magnitude. Okay, so kinetic energy equal to potential energy at the total energy, but minus of total energy. Clear? So these are the three important notes which is related to the kinetic energy, potential energy, and total energy. Okay. Now let's talk about the significance of this result. Look closely there at the total energy. It is negative. Okay. This negative total energy is incredibly important. It indicates bound orbits. So it indicates bound orbits. Bound orbits. What does bound mean? It means so here Earth, so here satellite. So bound means the satellite is gravitationally together to the Earth. Gravitationally attracted to the Earth. And it requires the external input of energy to escape from that orbit. Okay. So that satellite goes in that orbit like that, gravitationally attracted to the Earth. It requires an external input of energy to escape from that orbit. So if the total energy were zero or positive, the satellite would escape there. Again, I will say that if the total energy zero or positive means the satellite would escape the Earth gravitational pull and move off to infinity. Okay, move off into infinity. So as a student, you should be able to explain this point. The negative value of the total energy signifies a bound orbit and its implications for orbital stability. Clear? Okay. Now let's use a simulation to visualize this. I will share the screen once again. Okay, right. So we are going to use this simulation to explore one of the most fundamental principles of space travel, that is conservation of energy. Yeah, satellites orbit. We are looking at a 1,000 kg satellite orbiting Earth. Okay, right. So notice here, notice here, we have a eccentricity here, eccentricity, okay, 0.00 like that for a circular, which means our satellite is in a perfectly circular orbit. Let's look at the numbers on the right, like that. Yeah. So eccentricity 0.00 means circular. Okay. Now look at the energy components here. We have here three main values: kinetic energy, potential energy, total energy. Already you know that what is kinetic energy? It is the energy of the motion. That is K is equal to half mv square. The faster the satellite moves, the higher the kinetic energy. Yeah. And what is potential energy? In this case, it is gravitational potential energy. Already you know that potential energy value equation, that is minus G M E M by R E plus H, like that. Yeah. Okay. So it represents the energy stored in the gravitational field. Notice it is always a negative number. You can see that minus 2.55 G J. G J means gigajoules. Already you know that joule for energy. Yeah. So unit for energy, joule. So gigajoule means which is huge. So that's why we have to put G J gigajoule. Okay. So this negative number signifies a bound orbit. The satellite is trapped by the Earth gravity. Clear? Okay. Since a orbit is circular, okay, orbit is circular. The distance between Earth and satellite is constant. Yeah, constant. Okay. So, yes, satellite constant. And the velocity is also constant. So, in a circular orbit, all the three energies, that is kinetic energy, potential energy, total energy, are constant. Here you can see that. In a circular orbit, all the three energies constant. Kinetic energy, because radius constant, that is distance constant, velocity constant. So kinetic energy, potential energy constant. You can see that. Okay, right. So here total energy is the sum of the kinetic energy and the potential energy. 1.27 minus 2.55 gives minus 1.27. Okay, now let's see where things get interesting. We are going to change the orbit from circular to elliptical. For example, here you can see that eccentricity slider. Yeah, use a slider to increase the eccentricity to about 0.5. So now it changed into elliptical from circular. So 0.5 like that. Okay, for example, 0.5. Yes, 0.5. Now notice the orbital path immediately becomes a elongated ellipse. Yeah, correct. Which becomes a elongated ellipse. Now the satellite distance from Earth is constantly changing. Okay. Now I will again play. Now you can see that satellite distance from the Earth constantly changing. Yeah, you can see that. So this is the key to understanding energy conservation in orbit. Now look into the kinetic energy, potential energy, total energy bar. Values are changing. You can see that. But total energy always constant. That's why we can say that conservation of mechanical energy. Kinetic energy changes, potential energy changes because distance between the satellite and Earth changes, speed of the satellite changes, also changes. Now you can see that one point, that is perigee, which is the closest point to the Earth. Wait for the satellite to approach the perigee, the point closest to the Earth. Yes, like that. Yeah, okay. At this point, the satellite is moving the fastest because that is the point which is very close to the Earth. So the satellite is moving fastest. So its velocity maximum and also kinetic energy also maximum. So here, just to look at that. So satellite is there. Yeah. Kinetic energy 1.59 G. Okay. Now, once again, satellite approaching perigee point. Yes. Now, satellite approaching perigee point. Now, you can note down that is Kinetic energy value 3.81 gigajoule. This is the maximum kinetic energy because velocity is maximum at this point. Now, just look at that. Just look at that. Kinetic energy decreasing. Yes, decreasing because velocity decreases. So that's why kinetic energy also decreases like that. So green bar decreases. You can see that. Clear? So the green bar is the longest, that is kinetic energy is maximum when the satellite is moving in the mass past, its velocity also increasing when the satellite approach the perigee point. The distance r is at minimum because closest point means the distance, which is at minimum, which means potential energy at its most negative, that is its magnitude is largest. The orange bar is the longest. You can say that. So potential energy is at most negative, most negative. Now you can see that it decreasing. So this is a point, that is perigee point. This is a point where the satellite has converted the maximum amount of its stored potential energy into past working kinetic energy. Clear? Okay. Now wait for the satellite to approach the apogee. Apogee point means the point farthest from the Earth. Okay, farthest from the Earth. So that point does not appear in the screen because it denotes that point farthest from the Earth. Now the satellite is moving the slowest. So for example, yes. So the kinetic energy increasing and approaching. Yes. So, for example, we can say that this is a approach point. That is a furthest point. For example, we can take any one point. So, 0.72 gigajoule. Okay. Then the satellite moving towards the perigee point. So, kinetic energy minimum and the green bar is shortest. The distance maximum, potential energy closest to zero, and its magnitude is smallest. The orange bar is the shortest. When we play again, you can see that. Okay, good. So throughout this entire elliptical cycle, you can see that total energy, the red bar and the number remain constant. So this is the law of conservation of mechanic energy, that is kinetic energy plus potential energy, which is a total energy. Okay, right. So as the satellite swing towards the perigee, potential energy is converted to kinetic energy. As it swing out towards the apogee, kinetic energy is converted back to potential energy. So they are constantly trading off, but the total sum is fixed. Clear? Okay, right. So this is a simulation which is very useful to memorize the or understanding the concept of energy. Okay, total energy, potential energy, total energy, kinetic energy, and potential energy. Clear? Okay, right. Now here one important term, that is escape energy. Already I told you the escape energy is the energy required to make the total energy of the satellite zero, allowing it to escape from the Earth gravity. Okay, clear? So escape energy means it is the energy required to make the total energy of the satellite zero. So total energy means zero means it that satellites escape from the Earth gravity. Okay. Next point. orbital radius increases. Orbital radius increases, total energy becomes less negative. That is, it increases. Okay. So orbital radius increases, the total energy becomes less negative. So you can see that. Again, I will share the same simulation. Yeah. Okay. So for example, in this case, we can choose eccentricity 0.18. Clear? So 0.02, 0.11. You can see that the total energy increases. Is it clear? That is, the red bar increases. That is minus 1.27, which means negative. The total energy less negative when orbital radius increases. Clear? Okay, right. And next one. Okay, let's apply these principles, formulas with a couple of numerical problem. Problem number 1. A satellite, a satellite of mass 200 kilogram is orbiting Earth. A satellite of mass 200 kilogram is orbiting Earth at a height of 600 kilometer above the surface. So that means H above the surface. Okay, H. Calculate its kinetic potential and total energy. Calculate its kinetic and potential and finally kinetic energy. Clear? Okay. So here given data M mass 200 kilogram and H 600 kilometer. So H we have to convert kilometer into meter. So 600 into 10 power 3 meter. First of all, orbital radius. So orbital radius means radius of the Earth plus h, height of the satellite from the surface. So orbital radius R is equal to Re plus h. Already we know that the radius of the Earth value, that is 6.371 into 10 power 6 meter. So this is the exact value of the radius of the Earth. In some book, you can see that 6,400 for rounding off. Okay, but this is the exact value. 6.371 into 10 power 6 meter and plus h 600 into 10 power 3 meter. You can add that 6.37 like that. Ten power 6. So that's we can write like that for take the 10 power 6 as a common. Yes. So 6.971 into 10 power 6 meter. So this is the orbital radius. You have to find the energy. Before that, you have to know the orbital radius R, because R is very important in that terms. That is gravitational potential energy, kinetic energy. So gravitational potential energy. That is potential energy formula G M E by M by R. This is the orbital radius. So here you can put that values G, gravitation constant value 6.674 into 10 power minus 11. ME, mass of the earth. So exact value 5.972 into 10 power 24 kg and into mass of the satellite 200 by orbital radius. Already we have a value for orbital radius 10 power 6. So this is the joule, potential energy joule. Okay, right. You can simplify and you will get the potential energy approximately minus 1.14 into 10 power 10 joule. Note that value and you can do the calculations. Okay. So approximately we will get the minus 1.14 into 10 power 10 joule. So this is the potential energy. We have to find kinetic energy. Note it down. For circular orbit, the kinetic energy is exactly half of the magnitude of the potential energy. Already I told you. Kinetic energy is exactly half of the magnitude of the potential energy. So, for example, kinetic energy magnitude, okay, half of the magnitude of the potential energy. Because in the potential energy, we can see that negative side. But kinetic energy value magnitude half of the potential energy. Clear? Okay, right. So, kinetic energy 1 by 2 G M by R. Clear? Already we have a value for G M E M by R. 1.143 into 10 power 10 joule. So which gives approximately 5.72. Half of the 1.143 gives 5.72 into 10 power 9 joule. This is the kinetic energy value. And finally, total energy. Total energy means sum of the kinetic energy plus potential energy. Okay, right. So I will give the value of total energy. You can do the calculation later. Okay, because already we have a kinetic energy value, potential energy value. So for total energy, kinetic energy plus potential energy, 5.72 into 10 power 9 joule, and potential energy 11.43 into 10 power 9 joule minus. Okay, minus. So we will get the approximately minus 5.71 into 10 power 9 joule. This is the total energy of the satellite in this case. Clear? Okay. Please note it down. Okay. We will move into the next sum. Problem number 2. Compare the total energy of two satellites. Two satellites orbiting at heights of 500 kilometer and 1500 kilometer. Which orbit is more stable? Which orbit is more stable? Okay. So compare the total energy of the two satellites orbiting at the heights of 500 kilometer and 1400 kilometer, 1500 kilometer. Which orbit is more stable? Okay, right. For example, here So this is the H1, 500 kilometer. This is the H2, 1500 kilometer. Okay. For satellite number 1, height H1, 5500 kilometer. So orbital radius R1 means RE plus H1. So RE plus 500 kilometer. Yeah. For the satellite number 2, H2, 1500 kilometer. R2 gives RE plus H. So RE plus 1500 kilometer. Yeah. Here you can see that H1 is greater than H2. Sorry. H2 greater than H1. Yeah. Then it follows R2 is greater than R1. R2 is greater than R1. Yeah. So for the two satellite of the same mass, total energy, that is total energy, depends upon minus 1 by R, because that two satellite has the same mass and total energy depends upon the only orbital radius. Here you can see that the satellite 2 orbital radius, which is more, right? R2 is greater than R1. So the smaller radius R1 leads to more negative to not total energy. So I will write the hint. Smaller radius R1 leads to more negative total energy. That is, we can label it E1. Larger radius R2 leads to less negative. Already we saw that in the simulation. Yeah, less negative total energy E2. So less negative means the value increasing. Okay, less negative. R1 smaller radius leads to more negative. Larger radius leads to less negative. That is, value is greater. But in negative sign, it is denoted as less negative total energy. So the satellite in the higher orbit, 1500 kilometer, has a greater, that is less negative total energy than the satellite in the lower orbit, that is 500 kilometer. So E2 is greater than E1. Yeah, E2 is greater than E1 in the value of in the case of value. Okay, so E2 is greater than E1. Then, which is the term stability here generally refers to the longevity and resistance to the orbital decay. Higher orbit, that is 1500 kilometer. This orbit is higher above the Earth atmosphere. There is almost no atmospheric drag. That satellite requires very little or no corrective thrust to maintain its orbit. So this makes it more stable in terms of orbital decay. And lower orbit. So this orbit is closer to the fringes of the Earth's atmosphere. Even though the atmosphere is thin, a tiny drag force over time causes a satellite to lose energy and decay. So slowly spiral towards into the Earth. So this orbit, that is E1, R1, like that. This orbit is less stable. Okay. So 1500 kilometer orbit is more stable because it is less affected by the atmospheric drag, leading to much longer orbital lifetime. Clear? Okay. Now I will share the screen uh, 5 MCQ. Okay. Okay, I will share the screen now. Okay, right. First question, if the total energy of the orbiting satellite is negative, it means that what is the Uh, Answer. If the total energy of the orbiting satellite is negative, it means that. Why total energy is always constant? One student asked that. That is, it is a law of conservation of energy. Okay, good question. Okay, good. Two, two. If the total energy of the orbiting satellite is negative, it means that. Yes, very good. Yes, the satellite is in bound orbit around the Earth. Good, very good. Yes, bound to the orbit, bound to the Earth. Okay, good. Second question. When the height of the satellite's orbit increases, what happens to its total energy? Height of the satellite, already we saw that. When the height of the satellite's orbit increases, what happens to total energy? It becomes more negative, it becomes less negative, it remains constant, it becomes positive. Yes, two. Very good. Two, two. Yes, good. Yes, good. It becomes less negative. Great, great. Yeah, yeah, very good, very good. So orbital radius increases, that is height of the satellite orbit increases, the total energy becomes less negative. That is value increases. That's why I am putting increases in the bracket. Okay, right, good. Very good, student. And third one. Which of the following statement about the energy of the orbiting satellite is correct? I gave the hint in the class. Yeah. The kinetic energy is equal to potential energy. The kinetic energy is the half the magnitude of the potential energy. Kinetic energy is double the potential energy. Kinetic energy and potential energy are both positive. Which one is correct in the case of energy? Very good. Good. Three, two, one. Which one is correct? One, two. Okay. One means kinetic energy equal to potential energy. Okay. One kinetic energy half the magnitude of the potential energy. Two. Okay. Good. Kinetic energy is double the potential energy. One. Okay. We can choose one, but you can see that answer later. Okay. Okay. We can choose the one here because many of the students answer one. Yeah. Okay. Right. So fourth question. When a satellite is in a stable circular orbit around it, which statement is true? When a satellite is in a stable circular orbit around the Earth, which statement is true? The gravitational force acts toward and balance the satellite weight. The gravitational force provide the necessary centrifugal force of motion. The gravitational force and the centrifugal force act in the opposite direction. The satellite does not experience any force while in orbit. The satellite is in a stable circular orbit. Good. Two, 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 three, three, two. Yes, good. So here answer is two. Two. Yes, very good. The gravitational force provides a necessary, yes, two, yes, correct. Necessary centrifugal force of motion. Good. And the final one. What will happen if the total energy of the satellite becomes zero? What will happen? Already I told you. Yeah. If the total energy of the satellite becomes zero means it will move into small circular orbit. It will fall back to the earth. It will escape from the earth gravitational field, and it will remain stationary in orbit, stationary in space. What will happen if the total energy of the satellite becomes zero? It will fall back to the earth. Two. Total energy of the satellite becomes zero. Four. Okay. Four. Which one is correct? Four, two, or three, or one? Four. Okay. Let's see. Four. It will remain stationary in space. No. Okay, let's check. Let's check the answer. Okay, first one. So if the total energy of the orbiting satellite is negative, it means that the satellite is in a bound orbit around the Earth. Very good. So here again, okay, I am not selecting the option. Oh, that's why it shows error. Okay. when the height of the satellite orbit increases, what happens to total energy? It becomes, the option 2 is correct. It becomes less negative, that is value increasing. Okay, good. And third one, which of the following statement about the energy of the orbiting satellite is? The correct answer is option 2. The kinetic energy is half the magnitude of the potential energy. You don't look into the sign, that is positive or negative. Just look at the magnitude, that is value. The kinetic energy half the potential energy. So the kinetic energy half the magnitude of the potential energy. Clear? Okay. Next. Fourth one. When a satellite is in a circular orbit around that, which statement is true? Already you told that the gravitational force provides a necessary centrifugal force of motion. Good. And the final one, which is very important one. What will happen if the total energy of the satellite becomes zero? Many students answered that is it will remain stationary in space. No, it will escape from the Earth gravitational field. Okay. Option 3. It will escape from the Earth gravitational field. So energy is very, very important, which is should be in negative value. So suppose if the total energy is zero or positive, it means the satellites out of the Earth gravitational field. So that satellites escape from the Earth gravitational field. Okay, good, very good. So now your turn to ask questions. Any questions regarding that today topic? Any questions? Any doubt? Can you explain to the class why the total energy of the orbiting satellite is negative? Any student? Can you explain to the class why the total energy of the orbiting satellite is negative? Or anyone summarize the relationship between the kinetic energy and the potential energy of the satellite in a circular orbit? Okay, okay. No, no problem. Okay, excellent participation, everyone. Let's quickly summarize what we accomplished today. So the kinetic energy. Today we explored the energy of the orbiting satellite. Focus on the kinetic energy, that is half mv square per law g m e r e plus h. Potential energy minus g, sorry, get m e r e plus h. So half the energy in terms of value, and total energy minus of g m e m by r e plus h. Clear? Okay. So we learned that the total energy is negative, which is significant because it indicates a bound orbit. So, and we discuss its relation to the orbital stability. Okay. So finally, here is your homework. I will share the screen. Take it down. So this is your homework. Please note it down. Problem number 1. Derive the total energy expression for a satellite in a circular orbit, total energy expression, and calculate the total energy of the 150 kg satellite orbiting the Earth at a radius of 6,800 km. Use G and M. This is the mass of the Earth. Okay. Derive the total energy expression for a satellite in a circular orbit. And calculate the total energy of the 150 kilogram satellite. Clear? This is the first one. And the second one. A satellite is in a circular orbit around the Earth with a radius of 7,200 km. Calculate its kinetic energy, potential energy, and total energy. Then determine the change in total energy if the satellite's orbit radius increases to 10,000 km. So, satellite in is at 7,200 km. You have to calculate the kinetic and potential and total energy. then determine the change in total energy. Suppose if the satellite orbit increases to 10,000 kilometer. So very important question one. Okay. So here also you can use that G value and the M value. So this is all for today. Thank you, student. Thank you, teachers. Any doubts? Thank you. Thank you. Jai Vidyasakti, Jai Bharat, Jai Hind. Thank you all.